The strongest storm on Earth right now is not spinning in the Atlantic. It is not stalking the Gulf of Mexico. It is not hovering off the coast of Florida. It is roaring across the western Pacific, gathering strength over some of the warmest water on the planet, and scientists are watching it with a level of concern that should make everyone pay attention. What began as a messy patch of thunderstorms east of the Philippines has exploded into a super typhoon with the potential to become the most powerful storm on Earth this season. And if the latest forecast holds, its path could bring violent winds, catastrophic rain, and life-threatening storm surge into some of the most densely populated coastlines in Asia. The most alarming part is not just how strong this storm is, it is how fast it got there. In the time it takes most people to hear that a tropical system even exists, this one has gone from a developing disturbance to a storm that scientists say has the atmospheric ingredients to challenge the upper edge of what tropical cyclones can do. Today, we are breaking down the full picture. What this storm is, why scientists are so worried, how it intensified so quickly, which places are most at risk, what the forecast models are showing, and what this storm says about the bigger future of extreme weather. No filler, no drama for the sake of drama, just the facts, the science, and the full picture of what may happen next. If you want updates every time a major weather story like this develops, make sure you are subscribed to the Soccer Clock and turn notifications on. You do not want to miss real-time coverage when the stakes are this high. A thumbs up also helps push this information to more people who may genuinely need it. Now let us get into it. The storm that scientists are tracking started in a way that would have looked ordinary to almost anyone outside the meteorological community. A broad area of tropical convection drifted westward over the open Pacific, east of the Philippines and south of Japan, pulsing with scattered thunderstorms but lacking a tightly organized center. At first glance, it did not look like the kind of system that would dominate global weather headlines. Early satellite imagery showed bursts of convection trying to wrap around a weak, low-pressure center, but the structure was loose, the center was partially exposed, and the overall organization remained messy. To the public, it was another tropical disturbance in a basin that produces many of them. To forecasters, though, it was a disturbance entering a nearly perfect environment for explosive development. Sea surface temperatures were running exceptionally warm. Ocean heat content below the surface was deep enough that the storm would not immediately churn up cold water and starve itself. Vertical wind shear was low, meaning the atmosphere was not ripping the top of the storm away from the bottom. Mid-level humidity was high, which reduced the amount of dry air that could intrude into the core. And upper-level outflow, the exhaust system that helps a cyclone vent air away from the top of its circulation, was gradually improving. Put simply, the storm was moving into a lane of ocean and atmosphere that was built for rapid intensification. Once the core tightened, the clock started moving fast. Within a day, meteorologists upgraded the system to a tropical storm. Not long after that, it became a typhoon. Then it kept going. What followed is exactly the kind of escalation that now terrifies forecasters because it compresses the timeline between first warning and major disaster. The storm's winds climbed, the pressure dropped, the eye began to clear, and the cloud tops around the center cooled sharply, a sign that the thunderstorms feeding the cyclone were becoming deeper and more efficient. In a very short period, the storm transformed from a developing system into a classic super typhoon. The eye became symmetric. The eyewall tightened, the outflow expanded, the satellite presentation shifted from ragged to textbook. This is the moment when meteorologists stop talking about whether a storm will become dangerous and start talking about just how dangerous it may become. Scientists looking at the data describe the setup in stark terms. The environment ahead of the storm was capable of supporting extreme intensity. Forecast guidance began suggesting that the cyclone could challenge Category 5 strength or come very close to it. Some model solutions indicated a central pressure low enough to place it among the deeper systems observed in recent years. Others suggested the winds could climb beyond the threshold where damage is no longer measured in broken windows and downed trees, but in collapsed roofs, shredded power grids, inundated coastlines, and communities cut off from the outside world. And that is why the title of this story is not exaggerated. When atmospheric scientists say this could become the strongest storm on Earth, they are not talking about hype. They are talking about a storm forming in the basin that most often produces the most powerful tropical cyclones on the planet, during conditions that strongly favor rapid intensification, with structure and guidance that indicate the upper end of the scale is on the table. The Western Pacific has always been the heavyweight division of tropical weather. It is the largest and most active tropical cyclone basin in the world. The warm water is vast. The fetch over open ocean is immense. The storms that form here often have room to intensify for days before interacting with land. This is the basin that has repeatedly produced the strongest storms ever observed, including systems with astonishingly low central pressures and enormous wind fields. So when a storm in this part of the world starts deepening rapidly over hot water with low shear and healthy outflow, scientists notice immediately. To understand why concern is so high, you have to look at the combination of intensity and track. A powerful storm over empty ocean is still a meteorological spectacle, but the danger changes completely when the projected path begins intersecting with islands, shipping lanes, military infrastructure, dense coastal cities, mountain ranges vulnerable to landslides, and river systems that can flood far inland. That is where this storm becomes more than a weather story. It becomes a humanitarian, economic, and infrastructure threat all at once. The first places feeling that pressure are the communities lying closest to the projected path in the Western Pacific. Depending on the exact track, the outer islands south of Japan, parts of Taiwan, and sections of the Chinese coast could all face serious impacts. But forecast uncertainty matters enormously here, because a track difference of even 50 or 70 miles can change which communities take the eyewall, which ones see the strongest storm surge, and which ones avoid the absolute worst. That uncertainty is not a sign that scientists do not know what they are doing. It is the reality of forecasting a compact, extremely intense storm whose inner core can wobble, whose steering currents can shift subtly, and whose future depends on a complex atmosphere spanning thousands of miles. Right now, the broad consensus from scientists is that the storm will continue moving generally west-northwestward before eventually curving more toward the northwest. That sounds simple. In practice, it creates multiple high-risk scenarios. One track would bring the center close enough to the Ryukyu Islands and Okinawa to deliver destructive typhoon conditions, including intense wind gusts, pounding surf, and flooding rain. Another would take the core closer to Taiwan, where mountainous terrain can wring incredible rainfall totals out of a storm, even if the strongest winds begin to weaken. Another would push the storm toward the East China coast, where millions of people, major ports, industrial zones, and transport networks sit exposed to flooding, surge, and prolonged power outages. All of those scenarios are serious. The only question is, which communities end up on the worst side of the track? That is why emergency managers are already paying such close attention. For them, the challenge is not simply asking whether this storm is dangerous. That part is obvious. The challenge is preparing for the possibility that the storm strengthens even more before land interaction, while also communicating uncertainty honestly enough that people understand the threat without dismissing it because the exact landfall point could still shift. This is one of the hardest balancing acts in weather communication. If officials understate the risk, people delay preparation. If they overstate precision too early, later track shifts can undermine trust. The best forecasters understand that their job is not to predict one perfect line, it is to communicate a cone of risk and the consequences inside it. When scientists say the strongest storm on Earth may be coming, they are not promising one exact landfall city. They are warning that a storm with exceptional destructive potential is entering a populated part of the basin. Let us put some numbers around why scientists are using such serious language. Category 5 intensity begins at sustained winds of 157 miles per hour. Once a storm reaches that threshold, structural damage becomes catastrophic. But even before that, winds well below Category 5 can be devastating if the wind field is broad, the terrain is vulnerable, and the rain is relentless. Forecast guidance on this system has at times suggested sustained winds that would place it near the top of the typhoon scale, with gusts substantially higher. The central pressure projections have also been extraordinary, low enough to indicate a deeply intense cyclone with an efficient inner core. Lower pressure alone does not tell the whole story, but when it falls rapidly alongside tightening structure and exploding convection, meteorologists know the storm is entering dangerous territory. Then there is the eyewall itself. The smaller and tighter the eyewall in some major cyclones, the faster the wind can be packed into a compact space, creating an incredibly violent ring of destructive force. If a community takes a direct eyewall hit from a storm like this, the difference between being 10 miles inside the eye path and 10 miles outside it can mean the difference between severe damage and historic devastation. The eye can also be deceptive. People inside the eye experience a temporary calm, sometimes with blue sky overhead, only to be hit again from the opposite direction when the back side of the eyewall arrives. That is why every major storm warning emphasizes the same thing. Never assume the danger is over when the wind briefly stops. With a storm this intense, that false calm can be deadly, but wind is only part of the threat. In many tropical cyclones, especially near coastlines and mountains, rainfall and storm surge can become the most lethal hazards. Scientists watching this storm are concerned that it could produce enormous rainfall totals if the core interacts with terrain or slows near land. Moist tropical air forced upward by mountain ranges can turn already dangerous rain into a flood disaster. Taiwan is a classic example of this vulnerability. So are parts of southern Japan and eastern China. A storm that weakens slightly before landfall can still dump immense rainfall, trigger landslides, overwhelm drainage systems, and cut off towns long after the strongest gusts subside. Storm surge adds another layer. A powerful cyclone drives seawater inland, especially along low-lying coasts, bays, and river mouths. In some locations, surge kills far more people than wind because it arrives as a wall of water that can sweep through homes, roads, and entire neighborhoods. If this storm approaches the coast at high tide or with a broad wind field pushing water toward shore for many hours, the surge risk becomes severe very quickly. That is why scientists and emergency officials keep stressing that people should not focus only on the category label. The number matters, but the real hazard is the full package: wind, surge, floodwater, landslides, infrastructure failure, and the days or weeks of disruption that follow. One of the reasons this storm has drawn so much scientific attention is the speed of its intensification. Rapid intensification is not a vague media phrase. It has a technical meaning. It generally refers to a storm increasing its maximum sustained winds by at least 35 miles per hour in 24 hours. This storm appears to have met or approached that benchmark in dramatic fashion, and that matters because rapid intensification reduces the time communities have to adapt to a fast worsening forecast. A system that strengthens gradually over 5 or 6 days gives people a staircase of warnings. A system that jumps from modest tropical storm to major typhoon in 1 or 2 days turns that staircase into a cliff. Scientists have become increasingly worried about this pattern because it is appearing more often in some of the warmest basins on Earth. Tropical cyclones are heat engines. They draw energy from warm ocean water. The warmer the water, and the deeper that warmth extends below the surface, the more fuel a storm can access. If the atmosphere above cooperates, with low shear and efficient outflow, the engine can accelerate very quickly. That does not mean every storm will explode. It means the storms that find the right environment have the potential to intensify with stunning speed. And speed matters because emergency management depends on lead time. Every extra 12 hours can be the difference between orderly evacuations and last-minute chaos. Scientists are careful here because the climate discussion around storms is often oversimplified. The total number of tropical cyclones globally does not necessarily increase in a straight line every year, but what researchers have increasingly observed is that the strongest storms, the ones reaching Category 4 and Category 5 intensity, make up a larger share of all storms than they used to. They are also more likely in some regions to intensify quickly, and sometimes to hold peak strength longer. The physics behind that trend is not mysterious. Warmer oceans provide more available energy. Higher atmospheric moisture can support heavier rainfall. Rising sea levels can worsen coastal flooding when storm surge arrives. None of that means every single storm is caused by climate change. It means the background conditions are shifting in ways that can load the dice toward more dangerous outcomes. This storm is a perfect example of why that matters. It is not simply that one cyclone exists. It is that the environment around it appears unusually favorable for a storm to become extreme. Scientists often look for a chain of ingredients when judging whether a storm can become exceptional: warm water, deep ocean heat content, low shear, high humidity, strong outflow, a compact core, stable steering currents. This storm has checked many of those boxes. That is why it has become a focal point, and that is why so many forecasters are using words like explosive, dangerous, and potentially historic. If you live in a region that may be affected, this is the kind of wording that should trigger action, not curiosity. Another important factor is the time of year. The Western Pacific has a long and active typhoon season, and the peak months often deliver the strongest systems. When a storm like this forms before or during the core of the season, meteorologists also start asking a broader question. Is this a sign of what the basin may produce in the weeks ahead? One intense storm does not guarantee an extreme season, but active patterns can cluster. Warm ocean anomalies can persist. Large-scale atmospheric patterns can continue supporting development. And if a basin begins producing rapidly intensifying storms early, officials across the region have to start preparing for the possibility that this will not be the only major threat they face. For islands and coastal areas that are still recovering from earlier storms, that possibility is especially troubling. Imagine dealing with damaged roofs, weakened seawalls, exhausted emergency budgets, and stretched utility crews, only to see another major cyclone entering the same corridor before full recovery is complete. That compounding effect is one of the most underappreciated aspects of modern weather disasters. Communities are not hit in isolation. They are hit while already carrying the physical and financial stress of previous events. A storm that would be manageable for a fully functioning system can become a crisis when it strikes a region still operating on backup generators, temporary shelters, and disrupted supply chains. Scientists do not just watch the storm, they watch the vulnerability beneath it. This is especially true for islands across the Western Pacific. Many of them are remote, dependent on imported fuel and replacement parts, and limited in how quickly infrastructure can be restored after a major impact. Ports may close, airports may suspend flights, communications may fail, hospitals may shift to emergency power, fresh water systems can be disrupted, power restoration can take far longer than people on large continental grids might expect. A storm that cuts electricity to a major city is dangerous. A storm that cuts electricity to an isolated island and delays supplies for days can become a survival issue. That is one reason forecasters so often emphasize preparation, even when the exact track is uncertain. By the time uncertainty narrows, moving people and resources may already be much harder. Scientists are also studying whether this storm could undergo eyewall replacement cycles, a process common in major tropical cyclones where a second outer eyewall forms and eventually replaces the inner one. This can temporarily weaken peak winds, but it often expands the wind field, meaning the storm may spread damaging conditions over a larger area, even if the absolute top sustained wind drops slightly. For the public, that can sound confusing. How can a storm weaken and still become more dangerous for more places? The answer is scale. A compact monster may destroy a smaller area with incredible force. A slightly broader storm can expose a larger coastline to destructive winds, surge, and rain. That is why wise emergency planning never waits for a storm to weaken before acting. Sometimes weakening does not reduce the practical risk enough to matter. Model guidance adds another layer of complexity. Forecasters rely on a suite of models, each with different strengths, weaknesses, and assumptions. The American model may show one track, the European model may show another. Regional typhoon models may offer still more variations. Ensemble guidance, which runs models multiple times with slightly different starting conditions, often gives the best sense of the range of plausible outcomes. When the tracks cluster tightly, confidence increases. When they spread, uncertainty expands. Right now, scientists are trying to determine not whether the storm is dangerous, but which dangerous solution is most likely. A farther north track could spread heavy rain into Japan while sparing Taiwan the core. A farther south track could raise the odds of a severe Taiwan landfall. A more westward route could push major impacts deeper into the Chinese coast. Even a curve that keeps the eye offshore could still deliver pounding surf, marine hazards, and rainfall to wide areas. The point is not to memorize one model run. The point is to understand that the risk envelope is wide enough to justify serious preparation across multiple regions. Let us talk more directly about what scientists are actually saying. When meteorologists use phrases like life-threatening conditions, destructive core, major typhoon, dangerous storm surge, and rapid intensification, those are not routine words chosen for television drama. They are chosen because the atmosphere is signaling a storm that may surpass what many communities have recently experienced. Scientists are also saying that small changes in track or structure will matter immensely. They are saying the storm may weaken somewhat before final landfall, but that weakening should not be interpreted as safety, because rainfall and surge can remain catastrophic. They are saying anyone inside the cone of uncertainty should pay close attention to official updates, not rumors, not one social media map, and not one dramatic clip taken out of context. In other words, the scientific message is urgent, but it is also disciplined. Prepare early. Watch official forecasts. Do not lock onto one precise line. And understand that impacts often extend far from the exact center. There is a psychological trap with extreme weather that scientists fight constantly. People hear strongest storm on Earth and assume the message must be exaggerated. Or they hear possible Category 5 and think, I have seen storms weaken before, so this one probably will too. Or they focus on whether their city is on the center line instead of asking whether they are inside the zone that could flood, lose power, or take severe wind. That mindset is dangerous because preparedness is not about waiting until certainty reaches 100%. It is about acting when the consequences of being wrong are too large to ignore. If you wait until the storm is visibly on top of you, you are already late. That is especially true with rapidly intensifying cyclones because the forecast can worsen faster than people expect. The strongest storms also generate the biggest communication challenge once they approach land. People want simple answers. Where exactly will it hit? How strong will it be in my neighborhood? Will it weaken before it arrives? Will my house flood? Science can estimate these risks with increasing skill, but it cannot answer every local question perfectly days in advance. The atmosphere is too fluid, the terrain too complex, the inner core dynamics too volatile. What science can do is tell you when the risk is serious enough to demand action. And right now, that threshold has clearly been crossed. If this storm continues on its projected path, some communities will likely deal with destructive winds, serious flooding, and dangerous coastal impacts. Scientists do not need perfect certainty to say that. The data already supports it. This storm is also a reminder that the strongest cyclone on Earth is not always the one dominating headlines in the United States. Many people in the West are conditioned to focus on Atlantic hurricanes, but the Western Pacific routinely produces storms that are broader, deeper, and sometimes stronger than anything in the Atlantic basin in a given year. The names may be less familiar to international audiences, but the physics is the same and the stakes for the people in the path are just as high, often higher because of dense populations, steep terrain, and vulnerable coastlines. When scientists say the strongest storm on Earth is coming, they are speaking from a basin with a long history of producing exactly that kind of storm, and the storms in this basin do not respect national borders. One system can threaten islands, then Taiwan, then China, then inland provinces through rainfall. Another can brush Japan with outer bands while keeping its course south. Another can curve out to sea but still disrupt shipping, aviation, fisheries, and military operations across a massive area. That is why meteorologists track them not just as local storms, but as regional events with cross-border consequences. Governments start making decisions long before landfall. Ports review closures. Airlines consider cancellations. Utility crews pre-position assets. Military facilities secure equipment. Hospitals review fuel supplies. Evacuation centers prepare to open. None of those steps happen because officials want to alarm people. They happen because delay makes everything harder later. Even for places that avoid the core, the indirect effects can be significant. Heavy rain can destabilize slopes already saturated by previous weather. Coastal erosion can worsen from prolonged wave action. Offshore operations can shut down. Fishing communities can lose income for days. Freight can stall. Food prices can feel short-term effects where supply chains are tight. Insurance losses can ripple through already strained markets. A single major storm can leave marks far beyond the zones where the winds were strongest. That is part of why scientists and policy experts look at these storms not only as weather events, but as stress tests for modern infrastructure and disaster readiness. Another question many people ask is whether a storm this powerful can simply keep intensifying forever. The answer is no. Tropical cyclones have limits, though those limits can still be frighteningly high. As storms intensify, they can run into eyewall replacement cycles, interact with cooler water, encounter drier air, or face increasing wind shear. Approaching land can also disrupt the inflow that feeds the system. So even if this storm reaches extraordinary strength over the open ocean, scientists will keep monitoring whether the environment ahead remains supportive. But there is an important warning attached to that. Weakening from extremely intense to merely very intense does not mean the threat disappears. A storm can drop from the top of Category 5 to Category 3 equivalent winds and still produce devastating impacts, especially if it is large, wet, or interacting with terrain. That is why scientists hate it when the public treats weakening as an all-clear. It often is not. There is another layer scientists are discussing that rarely makes it into viral headlines, and that is uncertainty inside the storm itself. Intensity forecasting has improved, track forecasting has improved, and satellite monitoring is better than it has ever been. But the inner mechanics of a violent tropical cyclone can still shift faster than public expectations. A slight wobble in the eye, a burst of deep convection rebuilding one side of the eye wall, a temporary dry air intrusion that looks important and then gets sealed off, a small change in ocean heat content beneath the core. Each of those details can influence whether a storm peaks earlier, later, stronger, or weaker than projected. This is why scientists keep updating advisories even when the broad story seems unchanged. The storm is alive. It evolves hour by hour. That evolution matters most to the communities near the likely impact zone because local outcomes can differ dramatically over short distances. One town can take the strongest onshore winds while another, only a few dozen miles away, takes the worst flooding instead. One island can get the clean side of the circulation while another sits under the dirtiest quadrant for hours. One city can avoid the eye but endure catastrophic rain because the storm stalls nearby. This is not guesswork. It is how extreme cyclones behave. Scientists are also watching ocean feedback behind the storm because the wake it leaves can reshape conditions for the next system in an active basin. When a monster storm crosses warm water, it can churn the ocean enough to cool the surface behind it while leaving nearby untouched reservoirs of heat in front of it or off to one side. In a busy season, that matters. It influences whether the next disturbance entering the basin finds fuel or finds resistance. That is another reason this storm is being studied so intensely. It is not just an event. It may also be a preview of how the rest of the pattern behaves. In other words, the strongest storm on Earth is not only a headline about one cyclone, it is a warning shot about a basin that may still have months of energy left to spend. And for viewers far from the Pacific, do not treat this as somebody else's problem. The science being tested here applies globally. Every forecast lesson, every evacuation success, every infrastructure failure, and every communication mistake becomes part of the playbook other coastlines will depend on when their own extreme storm forms. Let us step back and look at the broader scientific meaning of a storm like this. Meteorologists have always known that the Western Pacific can produce giants. What makes modern storms more concerning is the context in which they are forming. Sea surface temperatures in many basins have been running above long-term averages. Marine heat content has been remarkable in some regions. Rainfall extremes are becoming more consequential as urban development spreads into vulnerable areas. Sea level rise makes surge more damaging because the starting point for coastal water is already higher. Population growth means more people live where storms hit hardest, so even if storms followed the exact same tracks as before, their impacts would not be the same. The The world beneath them has changed. That is why the phrase, "what scientists are saying," matters here. Scientists are not just describing one storm. They are describing a future in which the ingredients for severe weather can align more often in places that are more exposed than they used to be. They are warning that preparedness can no longer be treated as seasonal theater, something people think about only when a cyclone is already visible on radar. It has to be structural, better building standards, smarter land use, harder power systems, more reliable evacuation planning, more honest public communication. Storms like this expose every weakness all at once. They also reveal every strength. Because here is the other side of the story. Extreme storms do not automatically translate into extreme death tolls. Preparedness matters. Early warnings matter. People taking those warnings seriously matters. In many of the world's best managed storm responses, the most impressive outcome is not that a storm was small. It is that a huge storm caused far fewer deaths than it would have decades earlier because the systems around it improved. That is the lesson scientists and emergency officials keep repeating. Nature sets the hazard. Human decisions shape the outcome. The stronger the storm, the more brutally true that becomes. So what should people in potentially affected regions be doing right now? Scientists and emergency managers would say the basics, but they say them for a reason. Follow official forecasts from the National Weather Agency or recognized meteorological authorities. Know whether you live in a flood zone, storm surge zone, or landslide risk area. Charge devices early. Prepare water, medication, food, and important documents. If you are told to evacuate, go early, not late. Do not wait to see the weather deteriorate with your own eyes. By the time the ocean looks frightening, the roads may already be too dangerous. And if you live in a sturdy structure but near the coast, remember that water often kills faster than wind. Scientists are also saying something more subtle but equally important. Do not compare this storm casually to the last one you survived. People often anchor their judgment to personal memory. I stayed through the last typhoon and it was fine, so this one will probably be fine too. That is flawed reasoning because no two storms are identical. The angle of approach changes surge. The size changes coverage. The rainfall changes flooding. The eye path changes wind direction and peak force. The condition of your home may even be worse than it was last time. Scientists look at each storm on its own terms. The public should too. As for what happens next, the answer depends on the track and the environment in front of the storm. If it stays over hot water with low shear longer, it may hold exceptional intensity. If it interacts with an eyewall replacement cycle, peak winds may fluctuate while the wind field grows. If it clips one island chain before reaching a larger landmass, the core may weaken while the rain shield expands. If it slams directly into mountain terrain, winds may drop quickly but flooding may surge. These are the kinds of branch points scientists are studying hour by hour, and they matter, because each one changes which risk becomes dominant. What does not change is the central message. This is a dangerous storm. It is being watched closely because its upper bound is extreme, and several populated areas could feel severe impacts if current guidance remains in the same corridor. That is the full picture as scientists see it right now. A rapidly intensifying Western Pacific super typhoon has emerged in an environment capable of supporting extraordinary strength. Forecast models indicate a serious threat to parts of the region, with potential for destructive wind, torrential rain, flash flooding, landslides, and dangerous storm surge. The exact worst-hit location may still shift, but the threat itself is already clear. This is not a routine storm. It is the kind of storm that tests forecasting, preparation, infrastructure, and public trust all at once. If you found this breakdown useful, share it with anyone in regions that may be affected. Stay with the soccer clock for updates as the forecast evolves and as scientists refine what comes next. And if you are anywhere near the risk zone, take official guidance seriously, prepare early, and stay safe.